Okay, so in the last video we did a review of basic trigonometry. We talked about sine, cosine, and tangent. In this video we're going to use those skills to learn a little bit of some new math. And so we've talked about vectors before, but now we're going to get more in depth with vectors. Okay, so we know that as far as the definition is concerned, a vector is just a physical quantity which has both magnitude and direction. Okay, now geometrically speaking, you can represent a vector with an arrow. Okay, and so if you were to draw a vector, for example, you would draw it as an arrow. The magnitude of the vector, its size, is indicated by the length, and the direction of the vector is represented by whichever way the arrowhead is pointing. And so we can draw vectors as arrows, and the size or the magnitude of the vector has to do with its length, and the direction is whichever way the arrow is pointing. And the direction is also often represented by an angle with respect to, this is a little typo, some coordinate system, as we'll see. Now please make sure that when you're drawing all vectors, okay, including vector components, you draw them as arrows and not as lines. Okay, a lot of people get in the bad habit of drawing vectors as lines rather than arrows, but the direction is important because that's what separates a vector from a scalar, is the direction. Okay, so the direction of the arrowhead is crucial. Now, when you're working in 2 dimensions, you have to be even more careful with choosing a coordinate system to use with physics problems. Okay, and so there's some different coordinate systems we can use that I'll talk about. A very common type of coordinate system basically has the x-axis represent the horizontal direction, and then the y-axis represents the vertical direction. And so in that context, you would say, the positive y direction is up, and the positive x direction is just, to the right. Okay, now a different type of coordinate system you could use is north, east, south, and west. Okay, and so just to sketch these are both equally valid coordinate systems. You could say this is y, this is x. Okay, so this is the up direction, and then this is to the right. Or you could use a coordinate system like so, where you have just north, east, south, and west. And you'll see some problems with both of those coordinate systems. Okay, now when you're dealing with the north, east, south, west coordinate system, there is a specific convention for naming angles. Okay, in this coordinate system right here, it's most common to specify the angle measured between the vector and the x-axis, starting as measured going counterclockwise. So, for example, in the up-down coordinate system, if I had a vector over here, pointing that direction, it would be common to specify the direction by indicating this angle right here as measured from the positive x-axis. With the northeast, southwest coordinate system, the way we describe angles is we typically say something like north of east or east of north. Now, you might be asking yourself, what the heck is the difference between north of east and east of north? Well, the difference, I'm just going to erase one of these 2 coordinate systems so I can draw this again, but the difference between north and east of north is that if I draw a vector, let's say like so, notice it's an arrow, okay, so it has some direction and it has some magnitude which corresponds to its length. There's 2 different angles that I could use to specify which way this vector is pointing. I could either specify this angle right here, or I could specify this angle right here. And of course, they would both represent the same thing. However, if I were just to say 30 degrees, you wouldn't know which 30 degrees I was talking about. Okay, and so this is where the north of east or east of north comes in. When I say the north of east angle, I'm saying if you were to start off going to the east and then head north of there, that angle would be the north of east angle. So this would be north of east. On the other hand, this angle over here, if you start off going north and then you were to head east, that would be the east of north angle. Okay, so you have north of east, east of north, and you can use that for all the other angles. This angle right here would be the north of west angle, and then this angle in here would be the west of north angle. This angle in here would be the south of east angle, and so on and so forth. Okay, so pause there if you need to get that down and add that to your notes. It's something that always confuses people. Okay, so it might help you if you kind of draw a picture. Okay, so you understand, if I say 25 degrees north of west, 25 degrees west of north, those are two different angles. Now, those two angles I just mentioned are complementary to each other. So for example, if I indicate that the direction of my vector is, let's say, 30 degrees north of east, if I say that this angle down here is 30 degrees, then this angle up here would be 60 degrees because those angles are complementary to each other. So in other words, 60 degrees east of north and 30 degrees north of east indicate the exact same direction. Okay, neither of them is any more right than the other. It's just two ways of specifying the same thing. Okay, but make sure you understand that naming convention. Alright, so I'm going to erase this. Okay, this is just like a little picture to help you understand what I just talked about. North of east, east of north, west of north, north of west, and so on. Okay, so quick example with that. It says identify the direction of the vector shown in the picture to the left based on the convention discussed on the previous slide. So in other words, that 35 degrees in here, how would you name that 35 degrees? Okay, so this angle right here is, if you start off going west and then you head north, you would pass through this angle. So this would be the north of west angle. What about this 50 degrees? How would you name that? That would be the north of east. The 65 degrees, that would be south of west. And then this 80 degrees right here, that would be south of east. Okay, so pause there if you need to look at example 4. Now the main thing we're going to talk about in this video is what's called vector components. Okay, so make sure you take really good notes because we're going to be using vector components probably for the next couple months, probably through the end of the semester at least. Okay, so it's really important that you understand the concept of vector components. Okay, so let's talk about the concept of vector components. Let's say, for example, that I am in my house and I'm going to try to draw a picture. I don't know if it's going to work. And let's say I set up my coordinate system so my house is at the origin. Okay, so this is my initial position. And I leave my house and I walk 13 meters at an angle of 67 degrees north of east. Now, if I were to draw that vector, that's a displacement vector, by the way, because it's telling me how far I went. The magnitude is 13 meters, and then the direction is 67 degrees north of east. So if I were to sketch this vector, it would be something like this. Okay, the length would be 13 meters, and the direction would be 67 degrees north of east, and that's the north of east angle. Okay, so there's my picture. Now, with vectors, you can think of what's called vector components, and the word component basically just means piece. Now, what I want you to think of is, so I leave my house, I obviously end up here 13 meters from my house. Okay, is there another way that I could have ended up at that point? And the answer is yes, because I could have walked, along the east direction, and then I could have turned and I could have gone up in the north direction. All right, now this right here, I'm going to label this SY, and SY represents the Y component of my displacement vector. Okay, the S is for displacement, and the Y is for the Y component. And this down here, I'm going to label SX. Notice that these are arrows. This bottom arrow down here is pointing to the right, towards the east. This arrow up here is pointing towards the north. How did I know to draw those going to the north and to the east? Because my vector was going north of east. Now, let's say I want to know, okay, how far did I have to walk to the east? And how far did I have to walk to the north to end up 13 meters from my house? Well, if you look at how I set this up, notice that the components, along with the vector I started with, form a right triangle. So here's where that trigonometry comes in. Because I can say that sine of 67 degrees is equal to, remember sine is opposite over hypotenuse, so katoa, sine is opposite over hypotenuse, so sine of 67 degrees is equal to SY, that's my Y component of displacement, divided by the hypotenuse, which in this case is just the magnitude of my original vector, that 13 meters. And so SY, if I solve for that, that would be 13 times sine of 67 degrees. And I can just put that into my calculator, 13 sine of 67 degrees. And I get approximately, if I round up, 12 meters. And I can do the same thing with my x component. I could say cosine of 67 degrees. How do I know it's cosine? Because the x component is the adjacent side of this triangle, and the hypotenuse is still 13. So I can say cosine 67 degrees is equal to Sx, that's my x component of displacement, over 13. So Sx would be 13 cosine 67 degrees, and I can put that into my calculator, and I get about 5.1 meters if I round. Now, what do these values mean? These are my components of my displacement vector. Okay. Before anyone asks, is it always going to be displacement? No, because we've talked about different vectors. We talked about velocity and acceleration, and in the next unit we'll talk about force as well. Okay, so this is just, the first example we did with displacement. So what do these components tell me? Well, that means that, so I walk 13 meters, 67 degrees north of east. If I had wanted to, I could have just gone 5.1 meters to the east, turned, and then gone 12 meters north. Okay. In other words, my x component represents how much x my displacement has, and my y component represents how much y my displacement has, for lack of a better term. Okay, so pause it there if you need to look at that some more. Okay, so let's move on. Okay, and so we just saw our first case of vector components there. In this class, we are only going to do two-dimensional vectors. It's possible to have three-dimensional vectors, or I guess an infinite number of dimensions if you wanted to. Usually in college physics, you would do 3 dimensions, x, y, and z. We're only going to do x and y. And so there's two vector components, an x component and a y component, that basically describe how much of that vector is going in those specific directions. Okay, and not always, a lot of the time you can use trigonometry to find the components of a vector. Now, as we've seen so far, there's different ways to express a vector, and they're equivalent to each other. So in the last example, my original displacement, my original S, was 13 meters at 67 degrees north of east. That was a given in the question. Okay, I have a magnitude and I have a direction. Okay, that is my displacement vector. Now, I also ended up with an x component that was 5.1 meters and a y component that was 12 meters. And so I could also express a vector like that. I can also use what's called vector notation. And the way vector notation works is I'm going to draw an S. And by the way, I'm going to, just for now, I'm going to put arrows on top of these things. It's very common to see arrows on top of values that are vectors. And so when I see an S with an arrow over it, the arrow tells me it's a vector. And of course I know because we've been using displacement that S stands for displacement. So how does vector notation work? Well, it's kind of like an ordered pair, except that instead of parentheses, you use these triangle brackets. And instead of, like an x value and a y value, you have the x component, and then you have the y component. And so these triangle brackets indicate that these are the components of a vector, and the x component comes first, and then the y component comes after that. So these are three different ways of all expressing the same thing. Okay, you can either have the whole magnitude and direction just out there, or you can have the components separated out, or you can have it kind of like in this shorthand notation, this vector notation. Okay, so pause it there if you need to add that to your notes, which I would. Okay, and again, if you want to understand what a vector component is, I have a simulation which I want you to play around with. I will link it in the video above. But just to kind of give you a taste, basically up until now, all the problems we've been doing have been one-dimensional problems. And with one-dimensional vectors, it's very, very easy to indicate the direction. So here's a vector. Okay, this vector is called A. It's just like a generic name for a vector. And notice it's pointing to the right, and it has a magnitude of 10. Okay, notice up here we have the components. AX, that's the x component of vector A, is 10, and AY is 0. In other words, this vector has no y piece because no part of it is pointing in the y direction. All of it's pointing in the x direction. And so that's why the x component is 10 and the y component is 0. Now, what if I move the vector? If I decrease the length, notice that the x component changes, it gets smaller, and the y component is still 0. If I make it go in the opposite direction, notice now that the x component is negative 10 rather than positive 10. The negative sign here indicates the direction. So in one-dimensional problems like we've been doing up until this point, we can indicate direction by sign, either positive or negative. Okay, so what we're about to do now is move on to 2 dimensions in this class, which is why we're just now talking about vector components. So when we switch over to 2-dimensional vectors, okay, so again I just have a vector just kind of out here. Notice now that my vector is allowed to move in 2 dimensions. If it's pointing straight up, it has no x component because no part of this vector is pointing in the x direction, but it does have a positive y component. Okay. Likewise, I can make it point along the x-axis again if I wanted to, or I could have it point off any direction that I want, and then the components will adjust accordingly. Notice if I have a vector pointing kind of up and to the left, the y component is positive because the y piece of this vector, let me put the components on, the y piece of this vector is pointing up. The x component here is negative because the x part of this vector is pointing in the negative direction to the left, and you can see that little arrow down here. Okay, and so I can turn on the component mode so I can see the components. I can even have the values on if I want, and I can play around with this and see, if I go down here, I have a negative y component and a positive x component, and so on and so forth. Okay, this symbol right here with the absolute value bars, that just indicates the magnitude of the vector. Okay, so I will link that below. I want you to play around with that just to get a feel for vector components, because again, this is a concept that we're going to be using for a while. And then I'm just going to do a few quick examples before we finish the video. Okay, so we already did an example with a man leaving his house and walking along, but we can do another one really quickly. Okay, this one says man leaves his house and walks 18 meters at an angle 42 degrees south of east. Okay, first of all, the first question says what physical quantity is represented by this vector? This is once again a displacement vector. Now, how do I know that? Well, based off of the units. What is the magnitude of the vector? Remember, that's just its size. Okay, well, the magnitude of this vector is 18 meters. What is the direction of this vector? Okay, and again, it's very common to express direction with an angle. So I would say the direction of this vector is 42 degrees south of east. Okay, and that's the direction. Now for the vector components, here's where I need to sketch them. Okay, so I'm going to do a quick picture. I'm going to make a coordinate system where the house is at the origin. I don't have to do that, by the way, it just makes it easier to draw. And south of east is going to be pointing this way. So this is 42 degrees, the magnitude is 18 meters, and now I can do basic trig because I can see that the x piece of this vector is going to be the adjacent side to my triangle, and then the y component is going to be the opposite side of my triangle. And so I can say that sine, which is opposite over hypotenuse, of 42 degrees is equal to sy over sx. Now once again, why am I labeling this sy? You might be asking yourself, are all vectors labeled sx and sy? No. The s is because this particular example just happens to be a displacement vector, and the y is just to indicate that's the y component, the y part of this vector. So I can solve for sy, and then I can do the same thing with sx. Notice, by the way, that my y component should be negative. Okay, and the reason it's going to be negative is because it's pointing in the negative y direction. And so sy is going to be negative, I just did this in my calculator, 12 meters. And sx is going to be, let's see, 18 cosine 42 is going to be positive 13.4 meters. And so I would write this vector in vector notation. I would do my triangle brackets, and I would do 13.4 comma negative 12. Now I'll put the unit on the outside. So here are my vector components for example 1. So pause there if you need to look at that some more. Okay. A couple more quick examples. Example 1.5 says a car drives west with a speed of 25 meters per second. What physical quantity is represented by this vector? Well, this is velocity. Now you might be saying, wait, speed is a scalar, not a vector. And you'd be right. But notice it says it drives west with a speed of 25 meters per second. So here the magnitude is the speed of 25 meters per second, and the direction is west. That makes that a vector. And this vector is in particular velocity. Okay, saying how fast it's going and in what direction. Now what is the magnitude of the vector? 25 meters per second. What is the direction? West. What are the vector components of this vector? I want to see if you can figure this out on your own. Okay, so pause it here and try to answer example 1.5 on your own. Okay, so here's what you should have done is set up a coordinate system just real quick. And let's say this is the west direction. And so my vector is pointing to the west. The magnitude is 25 meters per second. And I'm going to label the components Vx and Vy. Now you might be thinking, oh wait, I should be using trig to find the components. But I actually don't have to do that here, because if you look at the vector and you understand the concept of what a vector component is, it's how much of the vector is going in that direction. So ask yourself, how much of the vector is going in the x direction? Well, all of it, because it's going to the left. All right, plus it's going in the negative x direction. And I would say that the x component would be negative 25 meters per second. And the y component, again, ask yourself how much of this vector is going in the y direction. None of it, because it's all going in the x direction. So the y component would be 0 meters per second. And so I would say v with an arrow over to indicate it's a vector. The components in component form would be negative 25, 0 meters per second. Okay, so those would be the vector components of that vector. Okay, so pause there if you need to look at it some more. All right. And I just want to do 2 more quick examples. A ball is kicked straight up into the air. Find the components of the ball's acceleration at its maximum height. Assume x is the horizontal direction, y is the vertical direction. So pause it here and try to do example 3 on your own. And the answer to this question, this is a concept question more than anything, should be 0, negative 10 meters per second squared. The ball at its maximum height, okay, it does stop moving up for a second, but none of that matters, because as long as the ball is in the air, it has a constant downward acceleration due to gravity that acts in the negative y direction, that acts straight down. Now, I didn't actually need the words maximum height in here, because regardless of where the ball is on its journey, okay, it doesn't matter if it's going up, down, maximum height, whatever, the acceleration due to gravity is still straight down. Okay, no part of that acts in the x direction, it all acts straight down. All right, and then I just want to show you one more quick thing. Most of the problems we've done so far is taking a vector that has magnitude and direction and breaking it up into components. Okay, but you can also go backwards. Given the components of a vector, you can also find the magnitude and direction. And so I'm only going to do a couple, well actually I'll do all of these really quickly. The first one, we have an acceleration vector, and we're given the components, and we're told that the components are positive 12, meaning that, this vector is going in some direction, but the x part of it is going in the positive x direction. And then the y component is negative 16 meters per second squared, meaning the y component is pointing somewhere down. So in other words, this acceleration vector is pointing somewhere down and to the right. Okay, so here is my acceleration vector. Now, how would I find the magnitude and direction? Well, if I know this is 12 and this side is 16, then I can find what is the equivalent of the hypotenuse just by using the Pythagorean theorem. I could say that the magnitude of A is equal to the square root of 12 squared plus negative 16 squared. And if you do that calculation, which I will do in just a second, I'm just plugging it into my calculator, you should get 20 meters per second squared. And so that is the magnitude of this vector, and the direction would be indicated by an angle. Okay, and so if you look at this angle that I've named right here, I have the side opposite to this angle, and I have the adjacent side as well. And so think what has opposite and adjacent, that would be tangent. And so I could say tangent of theta is equal to 16 over 12. You might be asking, wait, isn't it negative 16? Why are you putting positive 16? Well, that's a good question. I would highly recommend that you don't put negatives in when you're finding the angle, and the reason is I don't actually need the negative sign to tell me any information because I already know the direction looking at the picture is going to be south of east. If I put a negative sign in, I could get like a negative angle or something. And so rather than try to explain to you what that means by a negative angle, I'm just going to say when you're finding an unknown angle, forget about the negative signs. Just, do the normal calculation with positive numbers and then tack on the direction at the end. How do you find a missing angle? Well, in the last video, we talked about using inverse trig function. Because what undoes tangent, if we want to get theta by itself, we have to undo this tangent, is inverse tangent. And so if you do that to both sides, you get the inverse tangent of 16 over 12. And if you type that into your calculator, you get 53.1 degrees. And just looking at the picture I drew, that would be south of east. And so the answer to this question, find the magnitude and direction of the following vector. For the first one, the answer would be 20 meters per second squared at 53.1 degrees south of east, and that would be my answer. Okay, so pause it there, and again, that's just the very first one in example 4. Just in the interest of time, I'm not going to go through the other ones, but if you want to, you can use those for extra practice. And you have, of course, your practice worksheets for vector components. Okay, I would highly recommend that you get as much practice on this as you can, because we're going to be dealing with vector components for the next few months. As always, please let me know if you have any questions, and I'll see you guys in the next video.